Welcome to the exercises for Chapter 17. This chapter is focused on using integration to quantify geometric concepts like shapes and volumes and so on. So let's begin with exercise 1. This is a nice, gentle introduction to the exercises in this book because this one is not so difficult. Essentially, we are going to use SciPy to produce numerical approximations of analytically calculated areas between two functions. Okay, and in particular, what I want you to do is go back to figures 3, 5, and 6 in this chapter. Now, in those figures in the text, I used SciPy to determine analytic calculations, so to find exact solutions to get the definite integrals. And what you want to do here is use approximations in SciPy in the integration module of the SciPy library. Then you can calculate the net and total area, and you can check against the SciPy results. So I'll switch to code in a moment, but I'm only going to write code, or I'm only going to show you the code for figure 3. So let me first scroll up to figure 3. Here you see figure 3 from the main text. The two lines that you see drawn here are e to the minus x squared and x squared. So those are two lines, and then the area between them, using the bounds of 0 to 1, looks like this. So you can see it's actually divided into two pieces. We have one piece where f of x is larger than g of x, and a second piece where g of x is larger than f of x. And what we want to calculate here with SciPy is the net area and the total area. Obviously, the total area is going to be larger than the net area because we're going to have some positive area and some negative area. Or maybe this will be positive and this will be negative. Of course, that depends on how you set up the integrand, whether you use f minus g or g minus f. Okay, so here you see the code. This is code to create the two functions, f of x and g of x. Here I specify the bounds. Here I am numerically evaluating the result. So I'm using the substitution method plus list comprehension. And in this case, I'm going to need these to be NumPy arrays for calculations that I will make later for the numerical approximations. As I've discussed before, sometimes it's perfectly fine just to have this code here and have the output be a list. Sometimes you need it to be a NumPy array. In this case, we need a NumPy array. Okay, now the rest of the code in this cell is literally copy-pasted from the code that creates figure 3. So there is absolutely nothing new in this code cell with regards to this exercise. This just reproduces that figure. Instead, what is new here is using SPI.trapezoid to identify the net area that you see here within the bounds of 0 to 1 for the difference between these two functions, and the total area. And of course, the net and total area are nearly identical in terms of the code. The only difference is that we take the absolute value of all of the individual function difference values before inputting that into, in this case, I'm using the trapezoid method. So then we get the net area and the total area. Of course, the total area is larger than the net area. And that I say, of course, because the functions flip with regards to each other. So the sign changes. So there's negative area and positive area. So therefore, the net area will be a little bit smaller than the total area. And these values confirm what we calculated exactly analytically in the text, in the discussion around figure 3. Exercise 2 is about the fundamental theorem of calculus, part 2, and in particular, exploring the impact of calculating function differences, or the area between two functions within some bound, on the expression of the FTC2. So you know from previous chapters that the fundamental theorem of calculus part 2 states that the area between a function or a curve described by a function and the x-axis is given by the integral evaluated at the upper bound minus the integral evaluated at the lower bound. Now that is for one function, but in this chapter, you learned how to calculate the area between two functions within some x-axis bound. Now, the way that we have been expressing this is by subtracting two different functions. And we can come up with a new function, let's call it h, as the difference between f of x and g of x. Now, if we just think about function h, then the FTC2 is straightforward. It's still just a capital H, where capital H is the antiderivative of lowercase h. So h of b minus h of a. But what does the fundamental theorem of calculus part 2 look like when it's expressed using f and g and not expressed using h as the difference between two functions? So it turns out that here's the answer. So I call this delta A for the area difference between two functions within some bound. So f, uppercase f, is the antiderivative of function f, and g is the antiderivative of function g, lowercase g. Okay, so the difference in area is f of b plus g of a minus g of b minus f of a. Now, where does this come from, and how does this make sense? And how do we explain the differences in sign between this A and this A, for example? That is your first goal of this exercise. So essentially what you want to do is write down the fundamental theorem of calculus part 2. You can start with writing it down for h, and then substitute for h, f minus g, and then, just do some algebraic simplifications and confirm this expression over here. Once you have done that, then we want to implement the fundamental theorem of calculus 2 equations in SymPy, so in code, to demonstrate the equivalence between h of b minus h of a and this long expression that I had over here. Okay, you are going to do this using these two functions. So we have f of x, the function f of x is e to the minus x squared. And so capital F is the antiderivative of that expression. And the antiderivative g is the integral, the indefinite integral of x squared. Okay, so for these two functions, and using a equals 0 and b equals 1. This is actually the same two functions and the same bounds that I used in figure 3 and also in the previous exercise. But now here's the thing. The key part of this exercise is I do not want you to calculate the definite integral using sim.integrate with two inputs, where the second input would be the upper and lower bounds to evaluate the integral. Instead, what I want you to do is use sim.integrate just to get the symbolic expressions for the antiderivatives, and then use substitution on the SymPy antiderivative variables for these 6 functions, so h and f and g, evaluated at b and at a, in order to calculate these definite integrals according to the calculation specified by FTC2. All right, and then finally, you can use LaTeX printing in SymPy to print out the following results. So we have h of 1 minus h of 0 is the antiderivative of function h, which itself is f minus g. And yeah, here's what that looks like. So this these two terms here are h of 1, and then this is h of 0, and then, yeah, that just simplifies. And then here you can see I'm evaluating f of b plus g of a minus and so on. And the main point here is to see that these two expressions are the same. So again, this just gives you a little bit more conceptual experience with the fundamental theorem of calculus part 2. Well, it's going to take me a lot less time to show you the code than it did to explain the exercise instructions, because the exercise is a lot more conceptual than it is, requiring a lot of detailed code analysis. Okay, so here I specify f of x and its antiderivative, g of x and its antiderivative, and h of x and its antiderivative. Okay, and then here is where I'm setting up for the integration. It's actually not integrating per se because I've already done that here. But this is setting up or evaluating all of the uh, integrals at the bounds a and b. So I have fi, this is the indefinite integral or the antiderivative of function f, evaluated at a. So that's how you read this variable name. And so on for b, and then repeating that for functions g and function h. And then here is where I'm printing out the results. So there's a lot of LaTeX coding in here, but essentially, yeah, this is just showing the equivalence between these two expressions of the fundamental theorem of calculus part 2, whether we express one function, so function h, as the difference between f and g, or whether we explicitly write out this form of the fundamental theorem of calculus for both functions f and g. Exercise 3 was a lot of fun to create, and I hope you also enjoy working through this one. The goal of this exercise is to determine whether the upper lip or the lower lip in this image has a larger area. Now, visually, it certainly looks like the upper lip has a larger area, looks a bit fatter than the lower lip, but we want to quantify this, right? We want to make sure that it really is what we perceive it to be. So what are we looking at here? Well, here I've plotted 3 functions. And let's see, I'll zoom in, or you can see them here. So I have variable lambda for lips. We have f of lambda is the square root of the absolute value of lambda plus 3. And then g of x is lambda squared plus e over 2. And then we have lambda. H of lambda is the absolute value of lambda to the power of e. Just a bunch of weird looking functions that I came up with. But when you plot them on top of each other, they do form these interesting shapes. You can see that they all pinch, they all meet at not exactly the same value of lambda, but very, very close. So this forms 2 shapes. We can form 2 shapes between f of lambda and g of lambda, and between g of lambda and h of lambda. So there's a couple of goals to this exercise. First is to implement these functions in SymPy as symbolic expressions, so we can manipulate them and solve them and work with them and so on. And then what you want to do is find the values of these pinch points. Now it turns out that these pinch points are not solvable using SymPy. Actually, I believe one of these pairs of pinch points is solvable and the other one is not solvable. We will have a look at that in Python. I forget exactly which one it is. But suffice it to say, the points of intersection are difficult to find using SymPy. So therefore, the next part of this exercise is to find these intersection points empirically using numerical approximation methods that you learned about in Chapter 6 for identifying critical points and critical values. And that is what you see here with this figure. So what this figure shows is the absolute value of these function differences. So f minus g, the absolute value of that you see in the black line. Now you will remember from Chapter 6 that the points of intersection of the difference between these 2 functions corresponds to where the absolute value has a minimum. So where it is equal to 0, in theory, it should be exactly equal to 0. In practice, because we are discretizing these functions on a grid, you might not find a point that's exactly equal to 0, but you should find a point that is very, very close to 0. And that is our numerical approximation of the intersection between these pairs of functions. I showed you several ways to implement this in Chapter 6. One way is to use the SciPy function find_peaks. That's a great function. I use it a lot. I recommend you use it a lot. But for this specific exercise, I recommend not using the find_peaks function if you want an additional challenge. So if you want to make this exercise a little bit harder, then figure out how to identify these intersection points without using find peaks. Okay, and if you're really struggling with that, then use find peaks. As I mentioned, it's a great function. I don't normally recommend avoiding that function. All right, so that is the next part of this exercise, to identify these intersection points. Now, once you have the functions and you have the intersection points, of course, then you can calculate the areas of these two patches here. And to do this, you're going to find it difficult to implement this area calculation using definite integration analytically in SymPy. So therefore, I recommend doing this through numerical approximations in SciPy. Okay, so I hope that all makes sense. Let me see if there's another figure. Yeah, the final part of this exercise is just to print out the results here. So here I have the definite integral from, these are the intersection points. These are the two functions. And yeah, this one was approximately, this is the upper lip. This is approximately 5.26 squared units. And the lower lip was around 4.03 squared units. So this confirms beyond a reasonable doubt that the upper lip is a little bit more voluminous than the lower lip. Here I create a symbolic variable for lambda. I'm forcing this to be real valued because otherwise we're going to start running into some numerical issues. Here's where I define the three functions, f, g, and h. And yeah, I'm printing them out. Now, this was not explicitly part of the instructions, but it's always a good idea to print out equations and visualize equations and so on, just to make sure that you really have the code correct. All right, good. So now we have those. And now here's where I'm going to try to find the intersection points. Now, it turns out that F and G, SymPy was able to solve this analytically. So we could get an analytic solution for where these two functions intersect, but look at that. It took almost 30 seconds of computation time. Okay, so that's for F minus G, and let's see what G minus H gives us. Oh, okay, so we didn't have to wait very long, but we did get an error. It basically says no algorithms are implemented to solve this equation. So SymPy is just not able to solve this equation analytically. No problem. We are going to solve this empirically. The way that I do this is by first lambdifying these functions. This is useful for finding the intersection points, and it's also going to be useful for visualizing these functions. Okay, and then here's where I extract numerical evaluations of these three different functions in a range of our domain of -2 to +2 in 1,000 steps. Okay, now here is the point where we get the intersection based on the absolute value of the function differences. Now, this is the point where if you're struggling to come up with code solution here, you could just use the find peaks function. Totally fine. It's a great function. But the way that I chose to do this is by looking for where these function differences have their minimum point. Now, the thing is, we are actually looking for two minima. There are two solutions, right? You can see one is here, it's like -1.7, and the other one is here, is +1.7. So the code that I just showed will only return either one of these. So the way that I solved this part of the problem is by breaking up the function differences into two segments. So one segment that goes from -2 to 0, and then I'm looking for the minimum point there, and then I separately find the minimum point in the domain of 0 to +2. So that is going to give me this minimum point and this minimum point. And that is what you see here. So this variable fg intersect, this is where function f and function g intersect each other. You can see I'm creating this to be a list, and it's a list with two elements. This is the first element, and this is the absolute value of the difference between these functions from the beginning of the vector up until the 0 index, which is where lambda equals 0. And then I have, looks like exactly the same code, but notice the indexing is different. So here I'm going from 0 to the end. Okay, so this is for the first part, and this is for the second part of the function, so the second intersection point. But then this here is actually the function shifted. So the index value here is not going to be accurate. We need to add back on this offset value here of the 0 index. So I hope that makes sense. Gets a bit tricky with all of the indexing here, but this is essentially replacing what you would otherwise do with find peaks. Okay, so then we can print out these values and we see that they're around minus 1.7. It's not exactly the same intersection point for the two pairs of functions, but pretty close overall. Okay, so then, okay, so actually this plot here is just an intermediate plot. This shows the objective function that we are finding the minimum of to get the intersection points. And just to make sure this is all super clear, what we are doing here is finding where f and g touch each other. And that is going to give us the lower and upper bounds for calculating the definite integral between those two functions. And so, that's what we have. These are the lower bounds and these are the upper bounds. Very nice. Many steps here, but I hope you find that this exercise was more fun than it was frustrating. Let's see, the next thing to do is to approximate the areas between these pairs of functions using the bounds that we have just identified. And I'm going to do this in SciPy using SPI.Trapezoid. So here I define some convenience intermediate variables. So this is lambda for f minus g. So these are all of the lambda values that are between the intersection points for functions f and functions g. So where lambda is greater than or equal to the first intersection point and where lambda is less than or equal to the second intersection point, or the upper bound for our definite integral. Okay, so this is for functions f and g. Here's for functions g and h. Once you get this, the rest of this is really straightforward. You know all about this code here using SPI.Trapezoid. I'm just calculating the area between these two functions at these lambda values, or x-axis values, and this is the delta x. Okay, and then I'm just printing out the results using nice LaTeX formatting. And thus concludes the calculus part of this exercise. Everything left is just to generate the figure. So here I'm showing the three functions, and here I am showing the areas between those functions, and then some final touches to adjust the axis labels and so on. And there we go. And then, so you can play around with the colors. Let's see, these are particular colors that sorry, just a little typo there. Okay, let's see. Yeah, so here are colors that I like. Orange, because it's the color of the Netherlands, and purple, because, I don't know, purple is a great color. Exercise 4 has some conceptual similarities to the previous exercise, but here we're going to use SymPy a little bit more than in exercise 3. Okay, so here we have the function f of x is the natural log of x, and g of x is the function x times the natural log of x minus x. Now, g of x is actually the indefinite integral of f of x. In other words, when you integrate the natural log, you get x times the natural log minus x. Now, this is something that I discussed in earlier chapters, so this should be familiar to you. But what's interesting about this function and its indefinite integral is that they actually intersect exactly twice. And so it looks like this. It creates this really beautiful little almond shape here. And this means that we can actually calculate the area between these two functions, so between the natural log and its antiderivative, between these two intersection points. And that is the goal of this exercise. So here you want to work with SymPy as much as possible, although it's not always going to be possible. In particular, you won't be able to identify the intersection points analytically using SymPy. So therefore, you need to approximate them empirically, unlike in the previous exercise where I told you not to use the find peaks function. Here in this exercise, I encourage you to use the find peaks function. And once you get those intersection points, these 2 points here, Then you can calculate the definite integral using SymPy. And finally, create a visualization that looks like this. Here I define a symbolic variable x and the function and its antiderivative. Here I'm just printing out to confirm what we already know. This was not specifically part of the exercise instructions, but as I've mentioned like a bajillion times before, printing out functions and plotting is always a really good idea because this will help you find potential mistakes and bugs that may have snuck into your code somehow. Okay, so in theory, what we want to do is find the intersection between the function and its antiderivative, so between f of x and g of x. And what that means is finding the x values where the functions are equal to each other, which we can reinterpret as saying f of x minus g of x equals 0. So we want to solve for this equation. Okay, and now it turns out that SymPy is just not able to do that, which is fine. We are going to approximate a solution, or two solutions for the two pinch points. So here I'm lambdifying each of these functions, and then I'm also lambdifying the difference. Now, this is not specifically necessary. We could also just say fx minus gx, the lambdified version, so the numeric evaluation. But here I'm just showing you some different options. So here I'm creating a new function. This is, as if I'm writing h equals fx minus gx. And then here I'm lambdifying function h. So this, these two are equivalent to each other. Okay, but this is how I chose to write it. So now I have a new function, a Python function that comes from SymPy from lambdifying this function difference. And remember, we want to know where is this thing equal to 0? Okay, so we're going to evaluate these functions numerically. So, of course, we need to have an x-axis grid. And, of course, we are limited. We are bound by positive numbers here because one of these functions is the natural log. Or actually, both of them have the natural log in there. So then we find the peaks. It is minus the absolute value of the function differences. And then I put that into find peaks. Again, this is code and algorithms that I described in chapter 6 when I introduced empirical methods for finding critical points. Okay, so these are the peaks in terms of the indices, but we want to know the x-axis values at which those peaks occur, and I'm calling that variable pinch points. So now we can integrate, and it turns out that SymPy can integrate the function difference quite well once we know the intersection points. So these are approximations, but once we have those approximate bounds for the definite integral, we can integrate the area exactly. Okay, and I call this an optional plot because I didn't specify this in the instructions, but again, always a good idea to visualize everything that you're doing. Okay, so this blue line corresponds to the absolute value of the function differences, and where it touches 0, or at least where it gets as close as possible to 0, these correspond to the 2 points where the functions intersect each other. Now we are finished. We have everything we need. We can create a figure, draw the two functions, plot the area using fill between, plot the intersection points as dots, and then do some pretty stuff, including reporting the actual area that SymPy calculated. The goal of exercise 5 is to continue exploring the definite integral that we can define between the natural log function and its indefinite integral. So we start here from the fact that the natural log of alpha times x for some real valued number alpha, the indefinite integral, the antiderivative of this function is x times the natural log of alpha times x minus x. In other words, the scalar remains inside the natural log of the indefinite integral of the natural log function. So what we are going to do here is manipulate, systematically vary that parameter alpha. and explore the impact of that scalar value, that parameter, on the area between the function and its definite integral. So you can see two examples here. So here, so you should recognize the general form of the shapes of the functions and the area between them, this like really elegant looking almond shaped area from the previous exercise. What I am showing here is two examples of the same functions, so the natural log of x and its antiderivative, but with different values of alpha. So this is for alpha equals 0.4, and this one here, it's smaller and it's higher up, it has a bit of a higher angle. This is for alpha equals 5. Okay, so what you want to do in this exercise is vary the alpha parameter between 0.4 and 5 in, I think I said 33 steps. Yeah. So vary alpha 33 steps between 0.4 and 5. Create Python functions, so lambdafied functions from SymPy for the function natural log of alpha times x and its antiderivative. And then you can calculate the area between them. Now, to calculate the definite area between these two functions, you're going to need to identify the intersection points. And that's what you see here. Well, the intersection points are not specifically drawn, but you can see where they are here. And you know from the previous exercise that SymPy cannot solve for these intersection points analytically. So therefore, you will have to evaluate these symbolic expressions numerically, and you can use the find peaks function from SciPy in order to identify the intersection points, which become the lower and upper bounds for the definite integrals. Okay, now over here in panel A, you see the functions and the integrals. So the solid lines correspond to the functions, the dashed lines correspond to their antiderivatives, and the color corresponds to the value of alpha. Here I've drawn the function and its antiderivative and the patch, so the area that we are calculating, only for two specific values of alpha, the first value and the last value, so the smallest and the largest values of alpha. You can try plotting other ones. I think you will discover that if you try plotting all 33 of these, it just becomes a big uninterpretable mess. Okay, and then what you see here in panel C is a plot showing the relationship between the area, so the definite integral, and the alpha parameter. So alpha of 0.4 here, this one here, this area here corresponds to this large area here. And you can see that as alpha increases, the area between these two functions shrinks. So yeah, that you see here. Very nice exponential decrease here. Okay, so that's the main goal of this exercise. I have some additional suggestions, but I will get back to that after walking you through the Python code. So here is the for loop that basically implements everything in this exercise. We start before the for loop by defining values of x, similar to the previous exercise, although here I'm extending the x-axis domain up to 8, which is larger than the previous exercise because we need a little bit more space for the smaller values of alpha to pinch on the right. Okay, and then here are the alpha parameters, so 0.4 to 5 in 33 steps. And this is just initializing a vector where I will store all of the approximate areas. Okay, so here, inside this for loop, for each value of alpha, for each parameter value, I'm creating a lambdafied function of the function, so a Python function for the mathematical function, alpha times x for this particular value of alpha. And then also for its integral, here you can see I'm integrating that function. So this code here is exactly the same as this code. And if you like, you could have created a separate variable for the function that you would reuse these times. Totally fine. Multiple correct ways to solve this exercise. So lambda function for the mathematical function for its indefinite integral for its antiderivative, And here I'm getting a lambda function, defining a lambda function for the difference. So this is the natural log minus its antiderivative. Okay, and this is what I'm going to use to identify these pinch points where we get the intersections. Okay, so here in the first panel, the first axis, I'm plotting the function by or by x, and also its antiderivative by x. Here is where I find the x-axis values where the function intersects its antiderivative using find peaks. And I see here it looks like I implemented it as subtracting the functions. We could also do this with fdiff, this variable here. That's actually the same. Okay, and then here is where I'm using scipy dot quad to approximate the area of this difference function between these two x-axis values, so the lower bound and the upper bound. And of course, these two values are going to change at each iteration inside this for loop because the alpha parameter is changing at each iteration of that for loop. So then, yeah, here is where I make the final plot, the third subplot in the third axis. Here I'm plotting the alpha values by their areas, which I calculated up here. This code here is for the middle plot. So here I'm saying if we are at the first index or at the last index, that is when we create the middle plot, where I plot the function and its integral, and then importantly, the patch between them. So this is the actual area that we are calculating using scipy.quad over here. Okay, so let's see how all of this looks. And yeah, well, it looks like exactly how I showed in the book text. One thing I want to point out is that this code cell took around 4 seconds to run, and that's really because of all of the lambdification. Now, in general, whenever you can lambdify a function outside of a for loop, that's going to be better. That's going to be much faster. It takes SymPy some calculation time to lambdify these functions and to work with these symbolic variables. Now, in this case, these 3 lines cannot possibly happen outside the for loop. They have to be done inside the for loop for each value of alpha. But this is just something to be mindful of whenever you're writing code in for loops. Try to think about what operations are taking place inside the for loop that could be implemented outside the for loop. My final comment for this exercise is to consider exploring a slight modification to this function. So consider that here we were looking at the natural log of alpha times x, but the natural log of alpha times x squared is also a pretty interesting looking function. Now, the natural log of x is defined only for positive values, but the natural log of x squared, of course, can be defined for also negative values of x. Can be defined for any value of x except for x equals exactly 0. So you can try repeating this exercise for the function natural log of alpha times x squared. In that case, you can actually use a domain that goes into negative numbers, and you will find some interesting things that will lead you to making some decisions. So, for example, some values of alpha produce 3 intersection points, not just 2 intersection points. So that means some values of alpha are actually going to give you 2 areas and not just 1 area. How do you deal with that? Obviously, these are just personal choices because there's no right or wrong answer here. But pretty interesting, optional, additional exploration for this exercise. The goal of exercise 6 is to implement and visualize parametric functions. This is something that I introduced in this chapter. I showed you several examples of beautiful parametric functions in figure 9. I will scroll up to that figure in a moment. And the goal of this exercise is to write code in NumPy and Matplotlib that generates this figure. Okay, so here are the sets of equations. So for example, panel A in figure 9 is x equals the sine of 2t plus the sine of t, and y equals 2 times the sine of 3t, and t is this other variable that we use for creating parametric functions. And for panel A, I defined it between minus 2 pi and plus 2 pi. So this is for panel A. Here's the equations for panel B. And then we have C, D, E, and F. So if you want to take a screenshot or pause the video, now you can see all the functions. F in particular is pretty interesting because we have 2 to the power of the cosine of 9.844t, whatever that means. Here you see figure 9. And yeah, these are the drawings that we are going to create. These are the parametric functions that we will visualize by implementing the mathematical functions that I just showed a moment ago. And in particular, we can pay attention to this beautiful butterfly image here. We are going to work with this image in the next couple of exercises. We're actually going to use calculus methods to determine or to measure the length of this curve here, this line that creates this butterfly. So 6 sets of equations, and that leads to 6 of these panels. And now I'm also going to do something with redrawing panel F here. Now notice that I used a line. So I just used one black line to draw each of these objects, each of these parametric curves. And so the line has the same color everywhere, which is black. And that leads me to the next part of this exercise, which is to figure out how to use the plt.scatter function, so scatter in matplotlib, to create dots where each dot can have its own color that you can map onto one of the variables. And that will create a colored parametric function, which in this case looks like this. Once you see how to set it up, then you can play around and have a lot of fun trying to come up with different interesting looking color schemes. I like having colors in these plots. It really gives this a sense of 3D. This is just a two-dimensional function. There's no third variable, but it really looks like it has this kind of three-dimensional structure as if it were a weave or something. There are multiple ways that you can correctly implement this exercise. And that is one of the goals of one of my educational goals for this exercise, is to give you the opportunity to think and explore and see different coding solutions to these kinds of problems. So I will now explain my code solution, but I wanted to be clear that this is not the only way to solve this problem. It's just the way that I happen to think of. Okay, so what I did is to create a list of functions. So here we see the variable functions. This is a Python list. You can see the open bracket and the close bracket is down here. Now, each element in this list is a dictionary, and you know it's a dictionary because of the curly brackets here. So this is the first element of the list. Here's the comma, which separates the elements. This is the second element of the list, and so on. Now, each of these dictionaries in this list corresponds to the functions for a different panel. So I have a dictionary entry for variable t, and that's actually slightly different for each of these functions. And then for x and y, I set these up to be lambda functions. So it's a function of t. It's a one-line anonymous lambda function for x and for y. Okay, and now once I have all of those dictionaries, I can set up a for loop. So now I have a for loop where I'm looping over all of the elements in that list called variable functions. And then I can extract the data. So here I have variable t is the parameter for the key of t in this element of this list. And then remember that this here for y, this is a lambda function. So I'm evaluating that lambda function for these particular values of t. Okay, and then we have x and y, and we can just plot those. Pretty straightforward here. So I hope you found that interesting. If you solved it in a different way, then that's great. As long as you get the right solution, which is a figure that looks like this, then I'm happy and you should be happy too. Okay, and here's an example of using the scatter function. So here I'm just extracting the data only for one specific function. I'm just using list element 5, which corresponds to the sixth element, which is this curve over here, this parametric function here. Okay, and then I'm using plt.scatter. So I have x comma y. The S is for the size of each dot, and C is for the color. So the color corresponds to the value of t. So it's just going to increase linearly from the first point to the final point. And yeah, that's how I created this. So once you have this code, I encourage you to spend some time playing around with this. You know, maybe you want to make this, I don't know, how about t squared, just to give another option. You can set the color map to be purples. I think that's it, or maybe it's uppercase. I don't actually remember all of these color maps. Okay, yeah, this one also looks pretty nice, and so on. The very last thing that I want to encourage you to do with this exercise is to explore how incredibly sensitive to parameters these parametric functions can be. Okay, so let's see, I'll zoom out a little bit. Here's what this function looks like. Let's just work with this one here. Okay, so this is for panel F here. This function, you see what this looks like. All I'm going to do here is, maybe I'll change this to 9.6, and maybe I'll change this to 9.9. There's no mathematical theory for what I'm doing here. I'm just randomly playing around with numbers. But I'm only making really subtle changes to the functions, and that had a huge impact. That really had a qualitative change on the visual appearance of this function. So it's quite interesting to explore this kind of like really highly sensitive, chaotic, deterministic chaotic parameters. Now that we have created some parametric curves based on parametric functions, the goal of this exercise, exercise 7, and also the next exercise is to explore the impact of the resolution of the t variable on the estimated lengths of these functions. So in particular, what you are going to do is use the numerical approximation of curve length that I introduced earlier in this chapter to calculate the length of the butterfly curve. So that was the one you created in figure 9C from the previous exercise. That looks like this. So here you see the butterfly parametric curve. So you already have code to create this curve, the functions to create this curve that's from the previous exercise. Now what you want to do here is define this using delta t equals 0.001, and then calculate the length of this entire line, the whole function line, using the same boundary points that you used for the previous exercise to create this, this little curve here. If you use those same x-axis domain values, and if you set delta t equals 0.001, then you should find that the area of this curve equals 211.71, whatever these units are, centimeters, millimeters, there's no scale here, there's just arbitrary numbers. Okay, but you should be able to reproduce this result if you have implemented the integral correctly for approximating the arc length. Okay, and of course, this is not just one length. We actually measure the lengths of lots and lots of little sub-segments, little tiny segments, line segments, using Euclidean distance. These are all based on approximation methods that I described earlier in this chapter. What you see over here in panel B is a histogram of all of those lengths of those little tiny segments. So you have one little segment here, another little segment here, and so on. And that's going to give you, however many segments it ends up being based on this parameter value of delta t is 0.001. So if you are unfamiliar with looking at histograms, histograms is a way to examine the distribution of data values. It's often used in statistics and in machine learning as a way to understand the characteristics of the data that you're working with. Essentially, what we are doing is segmenting up the total possible lengths, so all of the possible lengths of these little individual line segments that create this curve, and then we count how many line segments anywhere in the curve are between this particular value and this particular value. So that's how a histogram works. Fortunately, you don't need to write the code to create a histogram from scratch, although you can if you want to. That's not a super difficult function to recreate. But instead, I recommend just using the hist function in matplotlib to create and display this histogram over here. I will have a few more remarks about these findings and what we have discovered here after walking through the Python code. Here I am defining the lower and upper bounds that we are going to use to draw this function, so 0 to 12 pi. And now here I'm defining delta t to be 0.001. This needs to be written as a separate variable because we want to manipulate this variable later on at the end of this exercise and also in the next exercise. Here I'm extracting the data. Now I'm using the function that I created in the previous exercise from exercise 6. So this was for the functions for panel B, or panel C. The only difference is here I'm redefining the vector t, right? So remember, actually, let me scroll up to the code from the previous exercise. So here we're working with panel C. Here I used numpy.linspace to define 1,000 points between 0 and 12 pi. But here I'm not specifying the delta t explicitly. It just ends up being whatever it ends up being based on this number of points between these two values. But for the current exercise, for exercise 7, we actually want to be able to specify the parameter delta t, and then however many points that ends up being. So therefore, in exercise 7, I'm utilizing part of the dictionary to get the lambda functions for x and y, and I'm redefining t based on delta t. Okay, then over here, I'm getting delta x and delta y. This is literally just the change on the x-axis and here on the y-axis from each point to each subsequent point in this curve. And based on those difference values, we can calculate the lengths of the individual segments as Euclidean distance. So the square root of the sum of squared distances between the x points, or the change in x and the change in y. Okay, and then here I'm just printing out the actual length. So let me see. Before I do this plot, let me just show you that what that prints out as. So with a delta t of 0.001 and the two bounds from 0 to 12 pi, that ends up being 37,000, so almost 38,000 individual points, discretizations that we use to create this function. And that gives us a total curve length of 211 units. Okay, so then we can generate the plot. I think this is pretty straightforward, just plotting x by y. And here I'm using a .hist, so plt.hist, and inputting all the segment lengths. This parameter 30 here is the number of bins. So you can see if I make this 7, 7 is too small. So that's going to give us only 7 bins. And yeah, you can make this like really a lot, like 190 bins. But this is also not super interpretable because we just have too many bins. So how exactly you pick an appropriate number of bins to create a histogram, that is a difficult question to answer. Depends on a variety of factors. It's something you would learn about in a course or book on statistics or machine learning. Okay, great. So what we can see here is that there are very few line segments that are really, really short lengths, and most of the segments have slightly longer lengths. Okay, and then it's also interesting, this will be the final exploration for this exercise. It's interesting just to change the value of delta t and see what happens to this length that we get here. So keep this number in mind, 211. What I am going to do now is just change this to 0.01 instead of 0.001. And what does this mean? This means that we now have a coarser grid on which we are evaluating this function, right? So now this function is based on fewer values, fewer numerical values, still between the same bounds. So the lower and upper bounds are the same, but there's fewer points. So now there's only about 4,000 points. And actually, yeah, okay, so it turns out to be almost exactly the same, still 211. Let's try and change this. Let's make it a little bit more. Don't want to be too dramatic yet because, oh, that still ended up being 200. Okay, let's be more dramatic. How about 0.1? Okay, here we get an area that is smaller. So a segment length that is now smaller than it was before, apparently 209. And you can also see that the butterfly is a little bit more rugged. This phenomenon of the length depending, so the length of this curve depending on delta x, is something we will explore in more detail in the next exercise. Here in exercise 8, we will continue exploring the approximated length of this curve here, this butterfly curve that we initially created in exercise 6, and then also explored the length of or wrote code to determine the length of that curve in exercise 7. Okay, so now in exercise 8, what we are going to do is systematically vary the delta t parameter. That is the resolution with which we evaluate the mathematical function to transform that representation, that sort of abstract math equation, into a reality, which is a curve that is drawn on a piece of paper, I guess if you print it out, so otherwise on your computer. Okay, so let's first walk through this figure, and then I will explain a little bit more about the details of this exercise. Let me zoom in here a bit. Okay, so panel A, you recognize the black line as the butterfly curve that you've now seen already several times. The light gray line with the boxes, that actually corresponds to exactly the same function, the same parametric function, the same domain for visualization. The only difference is that here with the black line, I'm using a delta t of 0.0001. And the gray line with the boxes, that is a delta t of 1. So quite a difference in resolution. And that has a huge impact on the visual appearance of this curve. In fact, if I would just show you this curve with delta t equals 1, you would not recognize it as the same butterfly function. That's how coarse that resolution is. Now, you might argue that it is inappropriate to draw lines between these points, but in fact, in this particular case, these lines really are justified because we are going to calculate the length of the curve based on the data that we have available. And the length of the entire curve is the sum of the lengths of the little line segments. And so these lines actually do depict the line segments connecting successive xy points, which we use to calculate the total curve length. Okay, so that is panel A. Now we get to panel B. What you see here is delta t on the x-axis going from 1 all the way down to 0.001. So in fact, this drawing here in panel A shows the two curves at the two extremes. So the smallest delta t that we simulate and the largest delta t that we simulate. Okay, and then, yeah, so I've reversed the axis just to make things look a little more interesting here. And then on the y-axis here, we have the curve length that is calculated using the integration methods that I introduced you to in this chapter for calculating curve length. Of course, we have to approximate the curve length here. We cannot calculate it analytically just because the function defining this curve is too complicated to analytically calculate. Okay, in general, ignore these 2 points. These 2 colors. I'm gonna talk about that in a moment. But if you just look at both of these functions, so NumPy and Simpsons, you see that they both increase as a function of decreasing delta t. Now, what does this mean? This means that the measured length of this curve gets longer when delta t gets smaller. Okay, so the finer the resolution, the larger or longer this curve, this parametric curve, appears to become. And this effect is quite dramatic. It's more than a twofold increase in measured length from the largest delta t, which is this really coarse evaluation of this function, to the finest delta t that I chose to simulate here, so we go from like, I don't know what this is, 90 something to 212 or whatever. So more than a twofold increase in apparent length of this function, depending on how finely we resolve the evaluation of this function. I will have some interesting interpretations to make about that after showing you the Python code. I want to just briefly highlight that there are two ways to calculate, or there are two ways that we are calculating in this exercise the length of this curve by direct implementation in NumPy and using Simpson's method. Now, the direct implementation in NumPy is the same thing that we did in the previous exercise. You just calculate all of the delta x's and the delta y's. You calculate the length of each individual curve segment as the square root of the differences between successive x values and successive y values, and then you sum all of those lengths, all those curve lengths. So that is the theory. That's what the sort of calculus theory tells us that we should do. But as you know from lots of examples throughout this book, that can be unstable. If you just directly implement the calculus concepts in NumPy, it can be unstable because you get these accumulating errors from precision errors that arise just from, coarse delta t or delta x on digital computers. Okay, so therefore, instead, you can also use Simpson's method, and so that's what you want to use here. So spi.simpson evaluated on the integrand of the square root of delta x divided by t, by delta t, and that quantity squared plus the same thing for y. Okay, and then, again, you can see that they are very similar, not identical. I will have more to say about that when I show you the code. And then finally, just to show you the parameters. So delta t varies from 0.0001 to 1 in 30 steps. So you implement this in a for loop over different values of delta t. Okay, so I hope that's all clear. Quite a lot of explanation required, but I believe this is now sufficiently clear. And now I will switch to Python and show you the code that generates this figure. Here I define the range of delta t's, so the different delta t's from 0.0001 to 1 in 30 steps. Here I am initializing the resulting arc lengths. This is for NumPy, so this is the direct calculation in NumPy. That's what the N stands for. Here is the for loop over the values of delta x. Now, this code here should look familiar from the previous exercise. In fact, I literally copy pasted it from the previous exercise. So here I'm defining the variable t, the parametric variable t, and then x and y using the functions that I define, the lambda functions from exercise 6. So this variable functions was created in exercise 6. And again, the domain is always the same for plotting. What changes with each iteration in this for loop is the delta t. Here's the differences, dx and dy. This I call the all NumPy solution. So these are the lengths of all the individual line segments, and then I'm summing them all up. Very nice. Now for Simpson's rule, here you can see this code looks kind of similar to this code, but here I do not scale by delta t in the all NumPy solution, but for using spi.simpson, we actually do scale by delta t. Now the reason why we need that extra delta t normalization factor in here is because we specify explicitly the delta t in the second input to spi.simpson. it's called dx here, but that's just the name of the input that it's expecting. So delta x for the inner workings of the function. Here I call the variable delta t. This bit of code here generates the plot. So here I'm just drawing x by y for when we are at the first index and when we are at the final index. So this is for the butterfly curve with the finest resolution, so the smallest resolution, the smallest delta t. And this is for the coarsest resolution, or for the largest delta t. Yeah, then the rest of this code is pretty straightforward. This is just updating the figure legends and labels for the first panel. And for the second panel, here I'm drawing the arc lengths defined in SciPy and then defined via direct implementation in NumPy. So again, here we reproduce the figure shown in the book. Now, what do we make of these differences here? Unfortunately, we don't know what is the true curve, but we can see that these results for Simpson's method looks smoother. So it does wobble around a little bit, but overall it appears to be less impacted by delta t in the sense that it appears to be a smoother function. Nonetheless, as delta t decreases, so as the resolution for creating this function increases, the two approximation methods are starting to converge. And that should be conceptually familiar to you from discussing in multiple cases, multiple chapters in this book about numerical approximations to true analytic solutions. And basically, the idea is that it doesn't really matter which algorithm you use, because at the limit, when you increase the resolution to infinitesimal, or increase the number of segments to infinity, all of these methods converge to the true analytic result. And that's kind of what we see here. So the differences between these different numerical approximation methods are larger for larger delta t's, and they start to converge for smaller delta t's. Now, you might ask, like, what is the true curve length? The thing is that in theory, out there in the Platonic world of math, we have some equation that defines this curve, and there is one unique curve length. This function with this domain from 0 to 12 pi, and these numerical parameters for the sine and cosine functions, it has exactly one unique length. It doesn't have multiple lengths. But here we are in the real world, and in the real world, we have to approximate these lengths using numerical methods. And then we find that the result, our approximation, can vary depending on delta t, which is like the length of the measuring stick that we use to cut out this function. In exercise 9, we are going to code and visualize an interesting curve called the folium of Descartes. We're also going to explore this curve in the next exercise. I will talk about that more when in the video for exercise 10. But for now, for exercise 9, the goal is simply to translate a mathematical formula that I'll show you in a moment into Python code so you can visualize the folium of Descartes. And we are going to implement this twice, once using polar coordinates and once using rectangular coordinates. So polar coordinates means that you have, instead of having x, y values, you have r and theta values, where theta is the angle, either in radians or degrees, although we will specify them in radians. And r is the radius at each point, so the distance away from the origin. So here we see the folium of Descartes. It's a pretty interesting curve. It comes down from the upper left and it goes down to the lower right. If you would zoom out, it almost looks like a straight line diagonal with a negative slope. But it does have this little interesting loop right near the origin, and it loops exactly once, it intersects itself at the origin, and then it continues along its merry way. So polar coordinates, where we specify r and theta for each point, and here are the rectangular coordinates where we specify x and y values for each point. Okay, so the formulas look slightly different. Here is the formula for r. So so the polar coordinates. So theta ranges from 0 to 2 pi, and r follows this function here. So it's a trig function of sines and cosines in the numerator and the denominator. Okay, so that is one way to implement this function. And then the second way is to implement it using parametric curves. So we define some variable t. In this case, I specified t to go from -10 to +10. And then here we have the coordinates for x and y in terms of t. Now it's interesting to note what happens when t equals -1. You can already see that when t equals -1, we're going to run into some trouble because we get a 0 in the denominator. So there's going to be some bizarre and interesting things happening around t equals -1. Now that is interesting because you can see that very clearly from looking at the parametric equations, but that's not really obvious from looking at the polar coordinates that anything particularly interesting is happening at t equals -1. Now, we have to be super careful here because this variable t is not the same thing as this variable theta. Those are completely separate variables. Okay, now there is a relationship between the sine of theta and the cosine of theta on the one hand, and x and y on the other hand. And that's because you can define x and y in terms of cosine and sine, and you can define, for example, sine in terms of x and y using circle, formula using Pythagorean theorem and so on. So here it's obvious that something weird is going to happen, and that's not necessarily so visually obvious when just looking at this equation. Okay, nonetheless, we will get back to these weird issues involving when the denominator here is around 0 in the next exercise. Don't have to worry about that for this exercise. Here in exercise 9, you just have to worry about translating those formulas into Python code and creating these two plots here. By this point in the book, I'm sure you are not going to have a lot of difficulties implementing this exercise. There's no calculus involved here, for example. So here I define theta to go from 0 to 2 pi. Now I didn't specify in the instructions how many points to use, so I picked an arbitrary value of 1001. And then, here is the function for r for the radius of each point. And I'm defining this function over two separate lines of code. I've mentioned, actually, this was something I discussed very early on, probably in chapter 3, maybe in chapter 2. But if you have a long function to write out, then of course it's possible to write it in one line of code, but splitting it into multiple lines is often beneficial because it helps you and other people interpret the code, look at the function, understand the function, and it reduces the risk of making little, honest coding mistakes. Okay, anyway, so this is polar coordinates. Here we have xy coordinates or rectangular coordinates, exactly as I showed in the formula. Here we have the plots. Generating a polar plot in Matplotlib is not difficult at all. You just need to specify when creating the axis that you have a projection of polar. Now, if you're used to creating 3D plots, for example, three-dimensional plots, then you would also recognize this general formula because this is also how you would create a 3D axis. Okay, so here we have a polar axis, and then we still use x.plot, but here instead of specifying the x and y values, we specify the theta and r values. Now, I have to admit, I often forget whether we specify theta and then r or r and then theta, so which order those get inputted into the plot function. If you are uncertain, no problem. Just, open up a browser and look up how to generate a polar plot, and then you will see the answer. Okay, yeah, and then the other one is easy, scatter x comma y. Okay, so that is pretty straightforward for the rectangular coordinates. Now, this is the figure as I show it in the book, but it's possible that your figure doesn't look exactly like this. In fact, your figure might have looked something like this. Let me or comment out these two lines here. You may have gotten plots that look something crazy like this. And what's going on here? Well, what's going on here is we have some very extreme values that are throwing off the rest of the plot. That is really clearly visible here in this plot. Check it out. This is the folium, the little bend, the little curve here is right at the center, and we have all these really extreme values here. Now, what's going on here? Well, these are the values that we get when t is close to -1. Remember that when t is exactly equal to -1, then we have a division by 0. But when t is not equal to -1 exactly, but is really, really close to -1, then this denominator here, both for x and for y, will become really, really tiny. This is going to be some very, very small number, which means that the fraction is going to become really, really large. So therefore, we get these extremely large values in this polar plot. And that's also reflected here with these very small number of very negative values here. Okay, so you can fix this issue just by setting the axes. So here I set the x and y limits to be from -5 to +5. So those extreme values of around -100 and +100, those are still in the data set. You just don't see them in this plot because I have specifically constrained the x and y axes for visualization. Okay, now, maybe that's not such an issue, but in the next exercise, we are going to try to determine the length of this curve. And when we include these extreme values here, that's going to change the length of the curve in interesting ways that have implications for applied calculus and curve length measurements. And that is the topic of the next exercise. At the end of the previous exercise, we discovered that there are extreme values in the folium of Descartes. And what we are going to do in this exercise is measure the curve length of the folium and consider that some of those extreme values, while being mathematically correct, are going to skew the curve length so much that we want to ignore them. So how do we ignore them, and which data values do we choose to ignore? This is an issue that we need to think about, that we need to work through in this exercise. And this is, something that comes up very often in applied mathematics, in particular, in statistics and in machine learning, in data science, when working with real data. Okay, so perhaps you are familiar with the term outlier. It's a term in statistics. It describes data points that are extreme. They are unusual for some reason. Maybe the outliers come from noise or equipment malfunction, or maybe the outliers are real, valid data, but they're so extreme, they're so different from the rest of the data that they can screw up all of your analyses. Okay, so in statistics and in machine learning, you need to identify outliers and figure out how to address them. And that's there are textbooks written just about that issue. Okay, so what we are going to do in this exercise is remove any line segments that are longer than 5 units away from the origin of the graph. So here is the origin of the graph in polar coordinates, and we can measure the distance of each point away from the origin using Euclidean distance. So the square root of the x-coordinate squared plus the y-coordinate squared. So that is our measure of length. And what I want you to do is remove any data points from the evaluation of the formula for the folium of Descartes that are greater than 5 units away from the origin of the graph. And then you can calculate the length of the curve based on all of the remaining points. So excluding all of these points that we have labeled an outlier according to this admittedly fairly arbitrary threshold of 5 units from the origin. Okay, and then we can make a figure that looks like this. So here we see the folium in rectangular coordinates, exactly the same as in the previous exercise. Here we see the functions x of t and y of t, with t on the x-axis, and yeah, here are the two parametrically defined functions. Now you see there's a funny gap here. There's some missing data points here, and this is because this is where we get values close to t equals -1, which means these are the values that are labeled as outliers. So these get removed from the data when we do our thresholding. Here you see the segment lengths as a function of t. Again, is blowing up to infinity, or at least very, very large lengths. And here, yeah, the plot cuts off here because, again, I've clipped data values. So there's missing values over here. Here we see the cumulative lengths of, so this is basically just the cumulative sum of this function over here, again as a function of t. And again, you see this flat area over here, and this is because these values of t close to -1 are missing from the data set because I removed them because they are outliers. Okay, of course, you should try generating this figure with and without removing the outliers to see what the impact is, and in particular, pay attention to the values on the y-axis. Okay, once you've created this figure, you can also calculate the curve length. I would like you to do this twice, once using a direct implementation of NumPy in NumPy as we did in the previous exercise, and also using SPI.Simpson. So 2 ways of calculating curve length, also as you learned in the previous exercise. And then, yeah, you can repeat this for with and without removing the outlier. You will see this has a huge impact, as I will show you in the code. So here we are in exercise 10. I am recalculating the x and y values. I don't need to recalculate t, but I am going to remove values of x that are labeled outliers. So therefore, I need to recalculate these so that each time I rerun the code, I get the original values of x and y. Okay, so here is the Euclidean distance, so the square root of x squared plus y squared. And this vector here, the result of this highlighted code here, is going to tell us the distance, the Euclidean distance, of each data point that we evaluated from these two functions to the origin. And here I'm saying that if they are greater than 5, they are going to be labeled as outliers. And this is let me run this and I'll show you this variable. So this is a Boolean vector, and it looks like this. So it's all false. You can see it's false almost everywhere. And there's a couple of values that are true. So where it is true, these are labeled, these are considered to be outliers. Okay, and why are they outliers? This is based on my admittedly fairly arbitrary threshold of 5. Okay, and then what I do is label all of the x and y points that are outliers as NaN. All right, and then, yeah, here I calculate dx and dy, and here is where I calculate the segment lengths according to the algorithms that you learned about in this chapter. So this is for the NumPy calculation here. Yeah, so then we just sum it all together. Now, these segment lengths are going to contain, actually, I can show you this as well. So these segment lengths, the individual segment lengths, are going to contain, what do I call this? I made it, I'm missing the G there. Okay. These lengths, so these are the lengths of each of the little line segments, but they do contain some NaN values, which you see here. And why are these NaN? Well, these are NaN because x and y contain NaN values. Okay, and what happens here is that when we try to sum all of these, so numpy.sum, we end up with a value of NaN because there is at least one NaN value in here. So therefore, there's a function in NumPy called NaN sum, and that just sums all the values except for the NaN. So it just ignores the NaN values. Okay, so this is curve length. The N here is for NumPy. Here is the curve length via Simpson's rule. And this code is exactly the same. And these two lines, so ignore this line of code for a moment. These two lines here are literally copy pasted from a couple of exercises ago. Okay, this is a new line of code that I've added, but it's commented for a moment because I want to show you what happens with spi.simpson when we have NaN values in the integrand. Okay, so then, yeah, here's the plots. I'm actually not going to take much time to describe these plots because nothing terribly interesting is happening there. Okay, so with the outliers removed, we get that the NumPy total curve length is around 14. So that is, with no extreme outliers. So the curve length, the curve starts here and it ends here. Now for Simpson's method, we get that the curve length is NaN. Okay, now this goes back to this issue here. So what I'm doing is spi.simpson is not built to handle NaN values. Okay, so therefore this is going to produce a value of NaN because the integrand contains NaN values. So that's why I have this line of code here where I say find all of the values where the integrand is NaN, so corresponding to outlier values, and just select for those, or select for the opposite of those, which means the finite values, and redefine, so overwrite the variable integrand to be only the values of integrand that are that have valid finite numerical values. And when I have that line, then you see we get a very similar result between Simpson's and NumPy's calculations. Now this minor discrepancy is basically due to the difference in algorithm between how Simpson's method works, and we can basically rely on this method more. This is likely to be more accurate than NumPy due to accumulating precision errors and so on, as I've discussed earlier. Okay, now I want to just show you how this changes when we do not reject any outlier values. So just to make things simple in the code, I'm just going to increase this to like 5,000. There's no data values that have a distance away from the origin of anything remotely that extreme. So that means that this is basically going to be an entire vector of false, which means there are no data points labeled as outliers. Okay, now this is not what I showed in the book, right? So I only showed the value or the results for with removing outliers. So first we can look at the plot. So remember before these values were cut off somewhere around here. Here you can see the curve lengths of each individual segment. So the segment lengths. We have a couple of really, really large values here. So this is mostly flat, or it appears mostly flat because the changes are relatively small. Here the changes are relatively small, and here we get a couple of extreme values that jumps this curve up all the way to 500 something. And yeah, then we see the curve length now is estimated at over 500. Here we see a larger discrepancy between NumPy and Simpson's method. And this is also similar to what you saw a couple of exercises ago when we compared Simpson and NumPy method for calculating curve length with different values of delta t, so different resolutions for defining the curve. In this case, the resolution is the same, but we have extreme values in here. Again, my inclination is to trust this number more than this number. But yeah, it's also pretty intense that we see the length of the curve go from being around 14 to around 520 just by having these extreme data points in here. Now, these are the kinds of issues that you will have to face if you are working with real empirical data and when to remove extreme values and what thresholds to use and so on. The purpose of this exercise was to highlight that these issues also arise in pure mathematics. Exercise 11 follows up from exercise 3. That was the exercise where we created a drawing of lips from 3 functions, and then we determined which of the 2 lips had a larger area by calculating the total area of the differences between pairs of functions. Okay, anyway, that was exercise 3. Here in exercise 11, we are going to focus on 2 of those functions, and I'll scroll up in a moment to remind you of those functions. And then basically what you want to do is revolve the area between those 2 functions, f and h, around the x-axis to create a solid of revolution. Then you visualize that solid, it looks something like this, and calculate the volume of that solid. And you should get somewhere around 131 cubic units. So that is the main goal of this exercise. I have another little sub goal, just to make it a little bit more challenging, is to shift the functions so that the intersection point is at 0. You might remember from exercise 3 that actually this dip here, this corresponded to lambda equals 0, this cusp point here. And now what I've done is shift the functions, both f and h, so that they meet at 0 instead of meeting at minus 1.71 or whatever that value was. Here you see the equations for f and h. These are the 2 equations that we are focusing on in this exercise, exercise 11. What you are looking at now is the text from exercise 3. Okay, so now let's switch to Python and I will walk you through my solution. Shifting the 2 functions so that their intersection, their left intersection, is at approximately 0 instead of 1.71 or minus 1.71 is fairly straightforward. It involves 2 steps. One is to shift all of the x values or the lambda values by that shift value. And here I'm just hard coding it to be 1.71. So we shift everything up, so to the right, positively by 1.71. You also have to keep in mind that you are now changing the bounds of integration. So previously in exercise 3, the bounds would have been something like this: a comma b equals minus shift val and plus shift val, okay? But now the new bounds are 0 and 2 times shift val. So that's with those changes, then that's basically all you have to do to shift the entire function on the x-axis, or as I call it here, the lambda axis. So here is where I define the 2 functions, actually redefining these because I've already defined them earlier in the for exercise 3. Here is the volume calculation. This you can write from scratch again for from how I described it in the text, or you can copy paste from earlier in this code file, in the code file for the chapter. So basically we have pi times the integral of, and here is where we're calculating the integral or numerically approximating the integral, the f squared minus h squared, and then we take the absolute value of that because we want the total area. Okay, which is actually not a problem here. Okay, and then, yeah, the rest of this is visualization, and this is all code that I have copied from previous figures in this chapter, and I'm just making very minor modifications here to get it to work for these variables that we have in this exercise. And here we see the final results. If you would like a little bit of an additional challenge here, you can repeat this exercise, but for the difference between the 2 other pairs of functions. So here we were working with functions f and h, and you can also repeat this for f and g, and then compare those volumes of revolution. The goal of exercise 12 is to calculate the areas of different geometric objects that do not come from a mathematical formula, but instead come from measured data points. Now, these are not data points measured from the world. These are data points that I created by clicking on the mouse and measuring the XY coordinates of the mouse. Anyway, the goal here is to measure the faces and vase created by something called Rubin's face illusion. Now, you might not be familiar with this term, but I think you are probably familiar with the visual illusion. So when you look at this figure, the question is, what do you see? Do you see two faces that are, facing each other? Here's the nose, here's the lips. They're very close to each other. Or do you see a vase or maybe, like a cup, an ornamental cup? So the cup here looks like this. So here, this would be the handle where you would grip the vase, where you would grip the cup. Maybe it's like an elegant wine cup from the 16th century or something like that. So I hope you can see both. It's a fascinating concept in psychology and vision psychology, about vision perception, about how the brain can resolve these two different images. A much longer story that I won't get into, but basically you cannot see both of these percepts simultaneously, but your brain is very good at swapping back and forth between seeing the two faces and the vase. All right. What we want to do is calculate the areas of these three geometric shapes. Okay, so the left face, the right face, and the vase in the middle that's created as the empty space between the two grayed out faces. And to calculate this, I want you to use the trapezoid rule from Riemann approximations. You should get, you should get that the total area of the vase is around 0.7, and the areas of both faces are the same at 0.629. And if you sum all of these three areas together, you will know whether you got the correct answers by the sum equaling exactly 2. Now, the sum should equal exactly 2 because that is how I created these data. And you can also see that just by looking at the axes on the graph. So the y-axis goes from 0 to 1. The x-axis goes from -1 to +1, so it's spanning a total domain of 2. So the total area of this figure is 1 times 2, which is 2. The first cell in this solution file is just a really long arrays of all the XY coordinates. So I have the Y coordinates, and then these are the coordinates for the X values of the right face and the X values of the left face. So you just run that code to get all the data. And then here in this next cell, I'm just plotting the data so you can see if this is exactly the same figure that I showed in the book. Now, there is a hint to get this to work, which is to flip the axes. So to swap the axes, swap the X and Y axes. And why is that helpful? Let me show you what that looks like, and then I will explain why this is helpful. I'll zoom out here a little bit. Okay, now when we swap the X and Y axes, we can think about the trapezoid rule by considering that each of these little segments here can create a trapezoid. So let's look at these 2 points here. The first 2 green points, this is coming from the left face. And then you can build a trapezoid going from the x-axis, which is formerly the y-axis, but when we flip the axes, flip the coordinates, we are considering the y values to be on the x-axis. So here we have the x-axis, and so this piece here going up to here. So these 4 corners here are going to create a trapezoid. So that means we can calculate the area. Maybe I'll zoom in intensely a lot here to make sure that this is, let's see. Okay, here we go. So now we are going to create a trapezoid that comprises this data point and this data point and this data point and this data point. Okay, so that makes one trapezoid. We can calculate the area of that trapezoid. Remember, the area of a trapezoid is the width times the average of the 2 heights. Okay, so this is the conceptual part, thinking back to Riemann sums. And where this gets tricky is that what I'm showing here on the x-axis actually corresponds to the y coordinates that I initially gave. So you have to just, yeah, it just takes some interesting thinking. Okay, and then I'll also conceptualize this to be a trapezoid here. This is like a trapezoid that's hanging from the ceiling instead of resting on the floor. But the calculation of area is exactly the same. And then finally, now let me just show here this example. So let's take these 4 dots here. Now we can consider this is not really a trapezoid here, it's a quadrilateral. So we can calculate the area of this quadrilateral here. That said, the area of a quadrilateral is equal to the base times the height of a square that's formed as the average of the quadrilateral sides. So the average of these 2 points here for the right face and the average of these 2 points for the left face times the distance between them. And that will give us the area of this quadrilateral here. Okay, I hope that all makes sense. That's difficult conceptually. I think that's the hard part of this exercise. So now let me walk you through the code. So here I am initializing the areas of these 3 pieces to be zeros. Here I'm looping over all of the values in y, which are going to become the segments. So here I calculate each individual part of the area formula. So we have h, which is the height, and then a and b, which are the 2 other axis coordinates. Now, h here is going to be the distance between each successive y value. Remember that when we swap the axes, when we think about this problem in terms of swapping the axes, then what I previously gave as the y coordinates, we are now thinking of as the x coordinates. So this variable h, you can think of as delta x, okay, when we swap the 2 axes. And then here is delta y, but this is not just for the right face. This is for the difference between the right and the left face. So the difference between this point and this point, for example, for each of these corresponding indices. Okay, so then we can calculate the area of the vase as being the base times the average of the heights. Here again, for the areas of the left and the right faces, yeah, this is also the average. Now, the reason why I have +2 in here is that we have to shift the calculation by 1 because here we have, this is actually starting at a value of -1, whereas we want to calculate this based on a value of 0. So we need to shift the axes by, in this case, -1. Here we need to shift the axis down by +1. But then because I'm calculating the average, so it's really, the average would look like this. And then we have to add 1, shift by 1, but then we multiply by h. So then we would need another set of parentheses in here. So it would look something like this, where this is just shifting here. So I just simplified the algebra a little bit to incorporate the 1, the shift by 1, into this formula. And then I had to scale it up by 2 because I'm dividing by 2 here, because we need the average of these 2 coordinates. I hope that makes sense. It's a little bit complicated. Okay, and that gives us our final area. The 2 faces have exactly the same area. The sum of the 3 areas is 2.